you very much, Axel. Thank you to Miss and Elisandra and Manuel for inviting me here. I'm very excited about this, and I've been loving the whole city and the institute and all the meetings we had so far. I hope I don't ruin this. So this is a paper I wrote for a special issue that Eduardo and Walter Corneli invited me to contribute to. And it's under revision at the moment. I hope I get at least a revise and resubmit, so then I can...
No pressure. So if anyone who's reviewing...
Exactly. But I hope so, because then I can incorporate the comments and the corrections and whatever comes up during this meeting, and particularly the Q&A. So I'm going to talk about truth in a logic of formal inconsistency. But in particular, let me just give you a quick introduction to the exact topic of my talk. The idea is that we usually want our theories of truth to be transparent, meaning that basically a sentence like rice is green and its truth predication, namely rice is green is true, we want them to be equivalent, right? So basically we want this to hold unrestrictedly, where I take this double arrow to mean whatever way of cashing out the equivalence you want. I don't care. Like, it could be a rule form, it could be a biconditional, it doesn't matter. We know that in any case, if we're working within classical logic, that brings us contradiction if we allow for self-reference of some kind. So if we can formulate a sentence like the liar, like a sentence that says of itself that it's not true, we will get this other equivalence, which is in direct contradiction with the first one in classical logic. And that would give us triviality. So this is a no-go. So people propose some solutions to the paradoxes that are based on two alternative diagnoses. The first one is, well, classical logic is wrong, it has to go, let's weaken it, let's do something else. And the other one is also basically that something is wrong, but we don't know what exactly. So, well, classical logic seems to be more or less right, and the truth principles that we want to add also seem to be more or less right, but something has to go, so let's try to make the smallest sacrifice. Some people say, just let some truth principles go. Like, I don't know, we could take Horwich to be one of these people, Halbach. And some other people say, well, let's let some logical principles go. And here we can have like Kripke, Field, Horst, Dave, a lot of people. This is kind of more popular now, nowadays. But people that can be found there are not people that necessarily, or at least the works of these people that I'm thinking about at the moment, are not such that these people are truly against classical logic. They think that classical logic is kind of fundamentally right, and that we only have to let it go when truth principles or other semantic principles are involved. And if we do so, the rest of the language would not be affected. So basically, we will only affect semantic reasoning by letting these logical principles go. So they say no biggie. But I'm not so sure that there's no biggie. And this is because of a recently published paper by, well, that is not the paper, by Halbach and Nikolai in 2007, it's not that one, where they say, well, there seems to be a problem actually here. It's not that simple. So this is the story. Halbach and Horsten have a paper in 2006, yeah, where they compare two axiommatizations of Kripke's family of fixed point models based on the strong clean evaluation scheme / LP valuations. They compare KF, which is the famous axiomatization of this family of models in classical logic. We'll see how that can work, given that the models are not classical themselves. And PKF, which is an axiomatization of the models in a more adequate logic, namely De Morgan logic. Actually, no, I'm not entirely sure. So can never remember, but it's either the Morgan logic or K3, which are very close to each other. It's the Morgan logic, yeah. So they, yeah.
Can I just ask, is De Morgan logic the sort of thing that sometimes gets called FDE?
No.
Is it?
I'm gonna.
Okay, you'll get.
Yeah. So the difference is the following, and this is going to be an important point later. The idea is that FDE allows for gaps and gluts, right? And so we have sentences that are both true and false, sentences neither true and false, or we can have that. But the notion, the logical consequence notion, is defined in terms of truth preservation or designated value preservation. Whereas in the Morgan logic is defined as designated value preservation from premises to conclusion and non-designated and untrue preservation from conclusion to premises. So it adds an extra requirement, right? So basically, for instance, in a logic like LP, you can have that an argument is valid if it goes from 1 to 1/2. But in the Morgan logic, you won't have the validity of that argument because 1/2 is falsity, but there's no falsity in the premises. So basically, truth has to be preserved from premise to conclusion and falsity from conclusion to premises. And if that doesn't happen, then that argument is not valid in the Morgan logic, whereas it would be in FDE. Is it clear?
So
No?
this is all over strong cleany stuff. Over the 3 values.
The Morgan logic is FDE. Is like it has the same family of models as FDE,
So
but the notion of logical consequence is
those
more.
are equivalent. The usual one and the one you just gave.
No,
What
they're
are
not.
equivalent? The truth preservation and falsity anti-preservation.
No, they're not, because you can have 1 to 1/2 in.
Oh, sure, but whenever you have a countermodel to one, you have a countermodel to the other.
Yes.
Right, so countermodels aren't necessarily the same, but the resulting consequence relations are the
Yes.
same. Okay, so that.
Yes. But not, you need to do some, yeah. All right, so they compare these two theories, and they show that KF is much stronger than PKF, which is to be expected because KF is a classical logic. But it's not only stronger with respect to the truth theoretic content, but actually with respect to the arithmetical content. So it does affect semantic reasoning, right? So basically, the restriction, the weakening of the logic does affect semantic reasoning. And this is what Haubach and Nicolai make of this. They say exactly this: the deductive weaknesses of PKF arises from the mutilation of classical logic, which invalidates certain patterns of mathematical reasoning that cannot be regained in PKF in any way. So basically, we lose mathematical content, which we say was not the case, or some people think it's not the case. So I was wondering, what if we decided to go for a different logic, right? A stronger logic. So let's exclude, first of all, let's start by excluding gaps. So let's go basically for something like LP and just demand that truth is preserved. Then LP contains all tautologies of classical logic, right? So maybe we can prove more stuff, because every time, for instance, a conditional gets value 1/2, or every time a formula gets value 1/2, in the case of the Morgan logic, in the way they are doing it, that thing won't be a theorem, but here it will. And therefore we'll have more theorems, and maybe now we can get some of the content back. Then I realized, because of what Dave just said, that it's a little bit hopeless, because there's a 1-1 correspondence between K3 and LP. So even though if I prove more stuff, I won't be able to use that information. So I thought, well, let's work with this. Let's work with our logics of formal inconsistency, which are logics that are designed to give us back all the classical reasoning that we might have lost by weakening classical logic. And they do that precisely in the places where we want to. So whenever we want classical logic back, they say you just use this wonderful operator these logics come with, and then you can get classical logic back. So this is the topic of the special issue. that I was invited to contribute to, which is just how just say something about logic of formal inconsistency, and I took it to be related to truth. And this is basically introduced by Cornelia and Marcos and Cornelia in several books and papers. What is a logic of formal inconsistency? It's a para-consistent logic, some para-consistent logic basically extended with a consistency operator. Given that there are different para-consistent logics, you'll have different LFIs, right? And also maybe there are different consistency operators that you can add. So there's a wide family. I'm gonna just be working with one of them. According to the creators, the LFIs can do this. The fundamental feature of the LFIs is the ability to recover all consistent reasoning right on demand, while still allowing for some inconsistency to linger otherwise. So the idea is precisely this, precisely what we want. Okay, let's have this operator to bring back the arithmetical content that was lost while keeping the non-classicality for the semantic vocabulary, right? That's exactly what we want. So the obvious question I want to ask today is, has the axiomatization of Kripke's family of fixed point models with a suitable para-consistent evaluation scheme in a corresponding LFI the same arithmetical strength as its classical counterpart or not? So can we recover the arithmetical content if we use an LFI or not? Seems like we should, right? So let's find out. This is the topic of the talk. So here is an overview. First, I know you're familiar with this, so I'm gonna go through an introduction to our basic para-consistent logic, to which we will add the consistency operator, which is LP, the logic of paradox. And so from a semantic point of view, and how we can have fixed point models in such a logic. I'm going to go through that very quickly. Then I'm going to present the two axiomatizations we will be comparing, right? So one is an axiomatization of the para-consistent Kripke fixed point models in LP extended with that consistency operator. That one is the one that has to be strong here, versus a suitable classical counterpart. So I'm going to present these two axiomatizations, and we're going to compare them in the third section. And then we're going to see whether we can recover classical logic or not. And then classical arithmetical reasoning or not. And then I'm going to draw some conclusions. If you have any questions, because now we're going to start with some of the details, technical details. If you have questions, please feel free to ask. All right, so you know this, but for notation, that L is a variable for languages, any first order language. And those are my logical symbols, and I'm going to give rules only for those. The other side are to be defined as always, as usual. And so what's an LP model? It's simply a usual structure that comes in a domain, an interpretation function that behaves standardly with respect to terms, like individual constants and function symbols. But when it comes to predicate symbols, it assigns an order pair, not just one extension, but an order pair consisting of an extension and an anti-extension. And they have to be exhaustive. So basically, every element of the domain has to be either in the extension or in the anti-extension of every interpretation. But they can overlap. So maybe there's an object of the domain or a sequence of objects in the domain that it's both in the extension and in the anti-extension of some predicate. Right? And this is a special predicate. And this special predicate, so since it's logical, it has to have a special clause. We only say that every object in the domain has to be self-identical, basically. Maybe it's also different from itself, but it has to be self-identical. So every order pair of the form AA for each element of the domain of the model has to be in the extension of the identity predicate. Okay? Now we know what a model is, how LP interprets a first order language. But what it is to be true in a model depends on an assignment, clearly, because we're working with a first language, we need to deal with variables. So let sigma be an assignment of elements of the domain of the model to the variables and extend it to all terms in the language. Then we evaluate formulae as follows. We have atomic formulae are true. I'm in class one. Atomic formulae get truth value 1 if the denotation of the terms belongs to the extension of the predicate, but not to the anti-extension. And vice versa, it gets value 0 when the opposite happens. And otherwise, it gets value 1/2, meaning if the tuple of elements of the domain belongs to both extension and anti-extension, then the formula is both true and false, 1/2. And well, negation, disjunction, and existential quantifiers are standard, as in classical logic, but now we have more values. And to be true in a model means that you get either value 1 or 1/2. So you're either true or both true and false. And for an argument to be semantically valid, it just means that for every model and every assignment in a model, if the premises get value 1 or 1/2, then the conclusion gets value 1 or 1/2. Right? This is simple, right? Now for the fixed point models. Now I'm working with a particular language, which is LPA, right? LPA is the language of first order arithmetic. It contains, it's just a particular first order language. It contains non-logical vocabulary, which is that 0, S, plus, and times. The intended interpretation is success, you know. And some finitely many function symbols for primitive recursive functions that I will specify later. N is the standard model of this language, and omega is the domain. So omega is a set of natural numbers, and this is just numerals. Basically, 0 is the numeral. A numeral is the name for a number. 0 is the name for 0, and then we have names for each number by iterating the successor function symbol just in front of 0, and then we get numerals, which we denote n bar. LT, which is the language of truth, language in which we will formulate our formal truth theories. It's just the extension of LPA with the monadic predicate symbol T. And this is just Gödel codes. If we have an expression of our language, which can be a term or a sentence or a formula, just any expression of our language, this is the Gödel code, and this is the numeral of the Gödel code of that expression. Cool. So we know very well that if that is a model of LT in which S is the extension, a classical model of LT, in which S is the extension of T, then this model cannot satisfy the T schema, cannot be a fixed point model, because that sentence will be true in the model for some sentence lambda, and therefore lambda and T lambda won't be able to get the same truth value in that model, right? Because that biconditional also has to be true. So basically there are no classical interpretations of our language, LT, in which each sentence and its truth predication are equivalent. So the original idea is not possible in classical logic. What about in LP? Now let's that triple be the standard model of arithmetic extended to LT again. But now the first set is the extension of the truth predicate, and the second set is the anti-extension. Remember, now we need those two. And then let phi, capital Phi, be a jump operator, which maps order pairs of subsets of natural numbers into order pairs of subsets of natural numbers in the following way. So basically what it's intended to map is extension and anti-extension of the truth predicate into extension and anti-extension of the truth predicate, into a new one, an improved one, not necessarily. That's the idea. So give me an extension, anti-extension, and I give you the new extension, anti-extension the following way. I put in the new extension all the sentences that were true according to the extension, previous extension, anti-extension, and all the sentences with negation was true in the model according to the previous extension and anti-extension, right? This is plus I add to the anti-extension all the things that were not sentences. This is what that means. The complement of the set of sentences. So I put in the anti-extension the non-sentences as well. There are some objects, there are some natural numbers that do not code a sentence. Those go in there. All right. If this happens, so basically if the sentences that were true according to S plus and S minus as extension, anti-extension, are already correspondingly in S plus and S minus. So they're all in S plus and the negations are already all in S minus. Then we have that identity, that fixed point. Then the order pair S plus S minus is a fixed point of phi, right? And therefore we say that this triple, this model, is a fixed point model of language. That's what it means to be a fixed point. And why is this important? Because in these models, every sentence and its truth predication get the same truth value. Not that there are no assignments there because we're talking about sentences, right? So assignments do not matter, but we could say for every assignment, phi and t of phi get the same truth value. So these models are very important. And here I'm going to show you that they exist. You know this proof how it goes. I'm going to give you a sequence of order pairs, extension, anti-extension, a transfinite sequence, whose first element consists of having everything in the extension and everything in the anti-extension. Second, you obtain it by applying the phi operator to the previous one, and the third one to the previous one, and so on and so forth. What do you do at the limit stage? You take the intersection of everything you had before. Okay? This operator is such that every order pair gives me a nice extension and anti-extension, meaning at every stage I have exhaustive order pairs. So every element of the domain of the model, of every natural number, is either in the left component or in the right component. So this sequence of order pairs generates a sequence of models of LP. They're all models. That's something important. The second important thing is that it's decreasing. So basically, once a sentence leaves, once an object leaves either the extension or the anti-extension in the sequence of models, it doesn't go back, right? So the intersection of extension and anti-extension is decreasing monotonically, right? This gives us a fixed point. Because at some point, we'll run out of things to take out from the intersection. Because we have a lot of time, right? Basically infinite, transfinitely infinite time. At some point, we'll run out of sentences. That would happen probably at Church's Plini's ordinal, and then we'll get a fixed point. Which means we have a fixed point model. Which means there exists an LP model in which every sentence and its truth predication get the same value. They're equivalent. So LP can accommodate transparent truth. This is fantastic. But this is a semantic construction. We want an axiomatic theory. Why? Because I'm an inferentialist and I think truth should be used. I love axioms, yeah. So let's see how to automatize this construction. As I told you before, I'm going to show you two axiomatizations. One is going to be in a paraconsistent logic, as seems natural, and the other one is going to be in a classical logic. And you think, oh, that's totally natural. Why would I do that? I'm going to give you reasons later. But first, let me show you how to first axiomatize LP, because on top of that, we're going to add the axioms of truth. But that's not entirely true. First, we're going to add the consistency operator, right? I'm going to give you a very rich, powerful, paraconsistent logic. And on top of that, the axioms of truth will come. All right, so Again, L is just any first-order language. The calculus of LP consists of the following rules: flexion, cut. This is just a rule for identity. For the identity predicate, this one is another one. This one is Leibniz law. That one is everything is self-identical. The standard rules. Then we have negation to the right. Basically means that we have exclude mill. This rule gives us exclude mill. Yes.
These are sets on either side?
Yes, sorry.
Thanks.
I wanted to say something about it. Thanks. Well, let's say it now. This calculus I'm presenting is something I made up to accommodate my interests and proofs. But it's very close to JC's multi-sequent, multi-conclusion sequent calculus for LP, and very close to Avron's. There are differences.
Actually, Avron's, I duplicated that. Avron's, the propositional one, mine's in effect the same, but the first order one is new, though not that interesting. You know.
All right. Well, that's why I took them off. I added these two rules for identity in this particular way. Usually we use sequence for that, just simple sequence. I added rules. This is because I'm following Negrian from Plato to give cut elimination proofs, because I need to prove completeness, and I wanted to do it via cut elimination because I had a lot of fun. I taught myself proof theory last semester, and I was reading a lot of books because I have a PhD student that works on proof theory and didn't know much about it. So okay, I had to do this, and let's put all the efforts here. And I learned a lot. I love this book, by the way, by Negrian from Plato. It's fantastic. So I need a rule form here. But it's equivalent to the sequence in the end. So if you prefer to work with sequence, then that's super fine. And this rule, I can use this rule. I use a horrible form of this rule. But this is the effect. So this gives us exclude mill. We can move negations to the right. We cannot do that to the left, because then we would get classical logic back. So this excludes gaps. If we had the converse of this, the introduction of a negation to the left, we would exclude gluts. We don't want that, right? Well, double negation we have, and the other rules are just the standard ones. I, of course, have rules for quantifiers because this is the first of the language. And, sorry, just one thing. Cut is, a weakening is admissible. And this is because there's cut there, which is part of the, cut is not, cut is part of the, is a primitive rule. And therefore weakening is admissible. And well, proof theoretic consequence is just what you expect there to happen, right? If we can derive that sequent, then we say that gamma proof theoretically entails phi. Is everything good so far? Well, then this is LP. And this can be shown to be sound and complete with respect to the semantics I gave you at the beginning. So it's fine. But we don't want LP. We want LP plus the consistency operator. So what we want is an LFI. And I call it LP circle. That's the system, this strengthened system. First, we need to extend the language with the consistency operator. So that's just L is any first order language. L circle is just any first order language plus the circle. And it's a monadic operator, so if phi is a formula, circle phi is also a formula. That's how it works. And an LP model is just, an LP circle model is just an LP model. It behaves the same. Now, how does the valuation function behave with respect to circled formulae? Just in that way, the idea is if the formula phi is 1/2, so basically it's both true and false, then phi is consistent is false. So it gets value 0. But if the formula is either 1 or 0, then phi is consistent is true. It's consistent is true, which means circle phi gets value 1. Note that circle phi always gets either value 1 or value 0. This is, we probably could do it somehow else, but this is how I chose to do it. And I think this is the strongest possible way, and we'll see why next. Now we need to, so that was the semantics. Now for the calculus, which is what we care about, we need to extend the calculus with rules. To understand the rules, I think the best is to work with empty contexts, which is a special case, and then you will see very well what's going on. Basically, it says that if we had if gamma and delta are empty, it says that if we can show phi and not phi, then we can show that phi is not consistent. But then we move it to the left, and that means that consistency phi entails everything, right? So it's a way of seeing it. If we have both phi and not phi, then consistency phi is false, so it entails everything. No, remember that consistency phi cannot be 1/2. So if it's false, it's 0, and therefore it does entail everything. And here, again, empty context. If phi and not phi explode, entail everything, then it's true that phi is consistent, because otherwise phi and not phi would be 1/2. And the others are just the same thing, basically, but with negation. This system is sound, strongly sound, with respect to the semantics I just gave you, and strongly complete, and this is via cut elimination. So this is why I prove in the appendix of my paper, cut elimination theorem, that gives us the strong completeness of the system. This is very important for the point I want to make later. That's why it's here. Oh, by the way, I'm not going to give you any proofs of anything. They're all in the paper. I don't want to bore you. They're very long also. The cut elimination proofs takes like 12 pages. All right, so why is this an LFI? Because it satisfies the definition that is given in Carnelian, Coniglio, Marcus, and Carnelian, Coniglio. What is a strong LFI? So there are two definitions that they give: normal LFI, strong LFI. Of course, it satisfies both, but most importantly, the strongest. So a logic is a strong LFI if and only if a bunch of things happen. First, we have two formulae, or formulae phi and psi in the language, such that A, phi and not phi do not entail psi. So basically, not every contradiction explodes. And also, this means basically that if just by the consistency of one of them, you also don't get everything. So it's stronger than it doesn't explode. Even if you assume it's consistent, you don't get that. And if you assume it's consistent, you don't get that from the negation. And then also, this does explode. So basically, once you have that phi is consistent, assuming phi and not phi does give you everything, right? So the consistency operator works as a consistency operator. And we can show that LP circle satisfies this definition. So it's a strong LFI. This is important. Now, how to axiomatize our theory of truth over this logic? That is very simple. We just need to work with our particular language of truth, but extend it with the new consistency operator. And the resulting theory is going to be called CKF for complete KF. KF is the name that the classical counterpart usually has. We'll see why later. And CKF is formulated on top of L circle. It adds arithmetical axioms and it adds truth theoretical axioms. As arithmetical axioms, we have initial sequence of that form where phi is a basic axiom of Peano arithmetic, basically an axiom of Robinson arithmetic, not quite, but sort of. Plus all the definitions we need for the function symbol for primitive recursive functions that we will add to the language. The language actually already contains. Then we have the rule of induction for every formula whatsoever. That doesn't hurt. But this is the important part. We won't just add arithmetical axioms and truth theoretical axioms as we always do. We also want to say that all the arithmetical part is consistent. And this is what this says. So we can prove, imagine empty context again, we can show the sequent consistent phi for every phi in the language arithmetic. So this is what's supposed to give us the strength of the theory, right? So if it's arithmetical, you can reason classically. That's what that says. All right, this is the truth theoretic principles. I'm not sure you're familiar with this. If you're not, just it really doesn't matter. You can spend some time later looking at them. This says that the T-schema, the transparency principles hold for atomic formulae. And this one says that truth and negation commute. This one that truth and conjunction, truth distributes over, disjunction. This one says that truth distributes over conjunction, or the negation of a disjunction. This one over existential quantifiers, this one over universal quantifiers, or negations of existential quantifiers. This one says that we can iterate the truth predicate. This one says we can iterate the falsity predicate. And this one says that only sentences are true. Remember, we put all the non-sentences in the anti-extension, in the model, in the fixed point constructions. So only sentences will be in the extension. And CKF harpoon is CKF restricted, with induction restricted only to formulae of the basic language, LPA. Right? So it's the same as CKF, but the rule of induction is not for every formula, but just for the ones that do not contain the consistency operator or the truth predicate. CKF is fully transparent. So we are capturing this feature of the fixed points that says that every formula is equivalent to a truth predication. We have all those sequences. And also importantly, CKF and CKF harpoon are both n-categorical, which means that if something is a model of these theories, then it's a fixed point model, and vice versa. But standard models, not every model. You know that. Arithmetic is not axiomatizable. So let's assume we have the standard model, then provided the fixed interpretation of the arithmetical vocabulary, the interpretation of the truth theoretical vocabulary is uniquely determined up to fixed points, right? So this is what, for instance, Fischer, Martin Fischer, Volker Halber, and who else is there? Johannes Stern and Johannes Speck in 2015 call a good way of capturing a family of models. So basically, this means that CKF is an axiomatization of the fixed point constructions we want to capture. Now, so I've shown you the non-classical theories. Now I'm going to show you the classical ones. Of course, as I said before, we're on Earth, like we're trying to axiomatize a family of prior consistent models using classical logic. Something must go wrong there. Sort of, but there's Reinhardt's idea. Because there's Kripke's construction and there's Pfefferman that axiomatized Kripke's construction in classical logic, and that's a very successful and famous theory that a lot of people love. And Reinhardt said this theory has to be wrong. How can we understand this theory called KF for Kripke-Pfefferman in a nice way? Well, the idea is this one. KF, Pfefferman's axiomatization in classical logic, is not a direct axiomatization of the class of non-classical fixed point models, but an external one, meaning everything that is true according to the theory, so what I call the internal logic of the theory, it's going to be true in all the models, in all the fixed point models of the family. It's not that everything the theory proves is true in every model, because the theory proves all classical ontologies, for instance, and well, that in LP wouldn't hurt, but never mind. But everything the theory proves to be true, it's true in the classical, in the family of fixed points. So, but why is it an external axiomatization? Because the classicality of the theory reflects the classicality of the meta-language when we specify the fixed point models. right? So that is an external axiomatization, as if it were an axiomatization from the meta language. So the internal logic is going to be actually paraconsistent, whereas the external logic is going to be classical, and this reflects the internal and external logics in the semantic construction. Another way of understanding the classical axiomatization of fixed point non-classical models is as follows, talking about the closing offs. So yes, KF, for instance, does not axiomatize a fixed point non-classical model like that one, but it does axiomatize its closing off, which is the classical model that extends the standard model of arithmetic with S plus as the extension of a truth predicate. So we forget about the anti-extension. Okay. And what we get is a classical model. And well, we'll see that the classical logic that I'm going to provide you as an axiomatization of the family of fixed point models we saw at the beginning is doing both this and that. So basically, the internal logic is going to be sound with respect to the family of models, and external logic is going to be sound with respect to the closing offs. Yes.
Just clarification. So, I started thinking about some of this and trying to think ahead. But so, are you saying that you have fixed point models for the truth predicate, so an actual transparent truth predicate with your consistency? Oh, okay, because I was gonna say, I'm completely lost. Okay, got it then.
So we axiomatize the family of fixed point models that we gave in a paraconsistent logic, but the family of fixed point models is given for the language LT, not LT circle. So we axiomatize it in LP, let's say, and that might be too weak. But then let's add the consistency operator to this axiomatization to be able to say that all the arithmetical stuff is consistent. But of course, the circle does not occur within, like inside the truth predicate, because we are axiomatizing the construction without the circle.
Okay.
There is no fixed point construction for the circle.
Yeah, okay.
That won't happen.
Yeah, for sure.
Yeah, of course. I mean, if we want to say, oh, but now that you're using LP circle, why not having fixed points for LP circle, for LT circle? And the answer is, well, you can't have that, because then you can get classical logic back. So you get paradoxes. All right. So the classical theory I'm going to introduce is called KFG. So it's like Pfefferman's, but it blocks the possibility of gaps. So we can have gluts and just gluts. So basically we have the same as for CKF, but now the axioms are come in pairs. So we have a positive and a negative axiom, because we cannot have the negation commutes with truth predicate, because that would give us the paradoxes back. So what we have to do is say how to have an atomic formula and how to build conjunctions, disjunctions, blah, 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 and then a negated atomic formula and how to build conjunctions, disjunctions, blah, blah. So everything comes in pairs. That is same as before, but everything in pairs. And again, only sentences are true. The interesting axiom is this one, which is the one we're adding to Pfefferman's axiomatization, which says, basically, you can introduce negation to the right. It amounts to saying that there are no gaps. If something is not true, then its negation must be. So nothing can be neither true nor false, right? This ensures completeness, right? All right, and KFG, as before, is just restricting induction to formulae of LPA. KFG harpoon is weaker than KFG. It's a subtheory of KFG, and it already implies Tn, which is half of transparency, right? So we can introduce a truth predicate, and it also implies T out, but restricted to arithmetical formula. So of course it won't imply T out, period, because that would demand having transparency in a classical setting. That's not possible. But we do have a good deal of transparency in our theory. And both theories are n-categorical. not with respect to the family of fixed point models, but with respect to the family of closing offs. So they're kind of nice, but not quite, right? They're external axiomizations. I think I'm gonna need 5 minutes more, but not much more. They're all external axiomizations, right? What we do have as a, what we do have as a real axiomatization, if you want, or what we do have that is sound with respect to, and then categorical with respect to the actual family of fixed point models and not the closing off, is the internal logic of the theory I just introduced. The internal logic is basically the set of things that can prove to be true in a theory. And the internal logic of K of G harpoon is the same thing, but for K of G harpoon, right? And I can prove n categoricity for this. So now, it makes a lot of sense to compare CKF and CKF harpoon, namely the truth theories formulated in LP circle, which were supposed to be strong, with these two, because they're both n-categorical with respect to the same family of models. And this is what we do in the last section. Well, I don't want to bore you a lot here, but this is how Cantini proves that a non-PKF, a non-classical theory of truth, can be relatively interpreted in a subsystem of KF. By introducing BT. I'm introducing here BTG. What is BTG? It's just take KFG, but replace the rule of induction with this rule, which is internal induction. Namely, just put like a T in front of for formally, right? You might say, well, this is the same as before. I just remove the T and I get what I had before. But of course, you can't remove the T like that. You don't have intersubstitutability of T and phi, a T of phi and phi, because otherwise you would have transference. So this rule is actually weaker. It is. This theory can only be proved to be equivalent to ramified truth up to omega to the omega, whereas KF is much stronger, as we'll see. Of course, you say, well, ramified truth, so I can only prove certain truth principles and not others. Sure, well, that's okay. Well, but this translates into arithmetical content. How? Like this. So if we can only iterate truth up to omega to the omega, that means that we can only have transfinite, truth theoretical transfinite induction up to this ordinal, which means that we can only have arithmetical transfinite induction up to a much greater ordinal, because PA already contains transfinite induction up to epsilon naught, so now we can do a little jump. We can go here in the Veblen hierarchy, but this is not, as we will see, very high. So transfinite induction, arithmetical transfinite induction is just an arithmetical principle. It's like 2 + 2 = 4, just a much more complicated and long. But it's just a theorem of arithmetic. This one can prove there are instances of this theorem up to that ordinal. Now, we can relatively interpret, and I won't go through this, but given this translation I'm giving you of the language of CKF into the classical language OT, given this translation I'm giving you, you can prove that if we can derive a sequent in your non-classical theory, you can prove that that sequent is sound in this BDG thing I just introduced. Why does this show that the sequence is sound? It says that if the conjunction of gammas is true, translation, all right, right? Because we have the circle in one language and here we don't. Then the disjunction of deltas is true. So basically, the sequence of CKF are truth-preserving. That's what BTG can prove. This means that everything that CKF can prove, BTG can prove. Translation. But in particular, everything that in the language of arithmetic that CKF can prove, BTG can prove. So basically, CKF is at most as strong, arithmetically strong as BTG. So basically, if CKF, if PTG can only prove instances of transfinite induction up to this ordinal, CKF can only prove that, and not more. So there's a limit for what CKF can prove in terms of arithmetical content. However, KFG can go up to epsilon naught for ramified truth, which is much higher than omega to the omega, which means that KFG can prove transfinite induction up to phi, not omega, but epsilon naught 0 in the Veblen hierarchy. But everything KFG proves, IKFG proves, the internal version proves, because we have T in, right? So if KFG proves something, we can add the truth predicate to that in KFG, which means that that's in IKF. Well, and also, we can show that CKF is a sub-theory of IKFG, which means that IKFG is stronger than CKF in terms of arithmetical content. It proves more arithmetic than CKF. And now you might say, well, but that could be because they have different truth principles, right? So we could blame this. We cannot blame this on the logic, because logic is complete and sound, but maybe we could blame it on the truth principles. We could say, well, I mean, we have less truth principles. We have different truth principles in CKF, but that's not true. And this is what this section shows. This is only one slide. Let's just look at the corollary. If we consider CKF, but with induction restricted to the sentences of the formulae of arithmetic only, without the truth predicate and without the circle, and IKF in the same way, the theories are equivalent to each other. Everything one can prove, the other one can prove. They have the same truth principles. The truth principles are identical. We only restricted induction in both cases. And in that case, the theories have the same proof-theoretic power. Therefore, we cannot say that it's because one of them has more truth principles than the other, that one of them is stronger than the other. And this is what I want to say, this last part. My conclusions are taken from Halbach and Nicolai. They prove analogous results for other theories, and they conclude the following. The incisions to classical logic, when applied to sentences with the truth predicate, severely impede schematic reasoning with the truth predicate. More specifically, classical patterns of mathematical reasoning are no longer licensed in PKF. So they conclude from these results, or from analogous results, that the reason why we lost arithmetical content is that we crippled the logic. So it doesn't come for free. It's not that the truth theoretic content won't be affected. This is what I say here. The weaknesses of our non-classical theory with respect to the internal version of the classical theory cannot be blamed on the incompleteness of the calculus underlying the non-classical theory, because I show strong completeness. And also they cannot be blamed on the truth theoretic content, because we saw that everything being equal, if we just restrict induction, we get the same results. It has to be due to the impossibility. It has to be blamed on the difference, the weakening of the logic. And the reason what's going on here is that in the classical case, induction containing the truth predicate works in full. We can extract all the consequences we want from that. Whereas in the non-classical case, if the truth predicate is there, we cannot generally apply modus ponens to it, because there could be gluts there. So basically, it's induction, the thing that is present in the one case and not in the other, that is weakening the theory. In one case, we can use induction because we have classical logic. In the other case, we have induction. We cannot extract consequences from that, because some instances contain the truth predicate. And once one of the instances contains the truth predicate, and that thing gets value 1/2, we cannot apply modus ponens, and we cannot extract enough consequences. So that's why Halbach and Nicolai say it impedes schematic reasoning, right? Once we we want to reason schematically. Some instances will contain a truth predicate. In the one case, we won't be able to work with that. So basically, we blame this on the mutilation of classical logic. And the last conclusion is that, well, after all, the consistency operator does not do what we want it to do, right? It doesn't give us back classical logic on demand. We're still struggling here. I'm going to leave this slide for the Q&A. It's about JC.
Yeah, so this is, I mean, I love learning this kind of stuff. Like, this is fascinating, but I'm trying to fit it together with the opening motivation, and I'm struggling a bit, and I'm hoping for some help in those lines. So I took the sort of initial motivation to be this thought about, like, hey, we've got, so we're thinking about arithmetic, so hey, we've got arithmetic, it seems to be working well. Now you have these wacky people who come along and say things like classical logic isn't the right logic, LP is the right logic, and we imagine trying to do arithmetic in LP, and we say, oh, that's going to be a disaster, we'll never be able to prove anything. And we say, okay, but don't worry, you can get back everything that you have in classical arithmetic with LP, right? And so this was meant to put some pressure on that.
No.
But yeah, it didn't put any pressure on that, right? Of course, because classical arithmetic doesn't have a truth predicate in it. So this is just my confusion. Was like, so I must have misunderstood that opening framing.
No.
Because there's no, as far as I know, no non-classical person has ever claimed that they can recapture, IKFG, because this is a brand new thing.
Sure.
So I'm missing, yeah, can you just help me see how the results fit that opening framing, or what the opening framing was that I misunderstood?
No, the opening framing is exactly that.
Okay.
It's just that I left this part for discussion, which is
Okay.
the idea that what we are losing is what we are not able to do in CKF is reason classically with certain instances of induction, right? The instances are new. We're not there before because now we added truth predicate. Before we didn't have truth predicate. I grant you that. That's why I think you're right. But the question is, do we want to reason classically with the new instances of induction? And the answer has to be yes.
Okay,
right?
why?
Because induction is an arithmetical principle.
But induction for truth isn't an arithmetical.
It's totally arithmetical. The induction, and this is why I said I'm leaving this for discussion. I'm willing to die for this. Induction.
Let's hope it doesn't go there.
It's up to you. Induction is something we believe for any predicate, even if we don't know the meaning of that predicate. It has nothing to do with the meaning of the truth predicate, that we accept instances of induction that contain the truth predicate. It is purely, it's because of our understanding of numbers that we accept induction openly, and not depending on on the understanding that we have of the predicates that occur on the instance.
Oh, but the difference here isn't over induction, right? It's over what follows from induction, over whether the extra exploitation that you get of induction is warranted or not.
Yes.
You've got full induction in CKF.
I do have, but I cannot, it doesn't, it's not classical. I cannot reason classically from it, but it's an arithmetical principle, and I cannot reason classically from it.
Ah, that's the line. Okay, good. Thank you very much. I think I see the difference here. Awesome.
Yay.
Well, Dave actually asked the same question, and he said he saw the framing. I guess I haven't seen it just yet. Could you repeat the last point about, so you have induction, but you can't reason classically from it because now you have gluts in the picture.
Exactly.
Do
you want me to give an example?
No.
Like I can write it down.
No, I'm confident of that. I guess I'm just philosophically,
I'm also puzzled about how to interpret this philosophically. I gather that, as I said today, we should be able to reason classically from that.
Well,
but at the same time,
but what does that mean? I mean, to reason. So I don't talk about reasoning very much because I truly don't know what it means. But I'm not trying to be a stickler about terminology. I really think reasoning is so wildly complicated that I don't think about that. So I just think of sort of what consequences do we want in our theory from that given principle. That I get, it's easy. But if you but when you were talking about reasoning classically, it sounds like you're saying we want things to be as if the good old classical picture is right. But the good old classical picture doesn't involve predicates that give rise to gluts. That you just, you walk away from that entirely. That's what Tarski does. So if you want classical reasoning to apply, then it's not a transparent truth predicate involved in induction in the way you want it. It's some other restricted truth predicate.
Yes.
So, but you can have detachment with restricted truth predicates. You might need a whole bunch of restricted truth predicates to get the consequences you want, but you can get detachment that way.
So it's tricky. It's yes and no, because in the case of IKFG has induction for every sentence in the language. And this is because KFG has. And KFG proves TN. Right? So basically you have induction for KFG and TN, so you can add the truth predicate to that instance of induction, and then that means it's in IKFG, because in IKFG everything that you prove to be true in KFG is in there, right? So IKFG has induction for everything, but it also has transparency. So IKFG is n-categorical with respect to the family of fixed point models of LP. So in IKFG you have both transparency and induction. And it's there where you prove more arithmetical claims than in CKF. Of course, it also happens in KFG, but I'm not comparing those two because I gather that's unfair, right? I'm comparing only the internal one with CKF. So the truth predicate is transparent here.
Yeah, fine. So you brought in a transparent truth predicate to do whatever work it's supposed to do, right? Okay. But it gets in the way of having consequences from certain induction principles. It's not going to serve the role of a truth predicate that you want in your classical reasoning from induction principles. So you bring in another truth predicate to do some of that work. This is a philosophical point. We have to walk very carefully through the technical stuff, but I'm just trying to get on board with kind of what the issues are. I mean,
I understand. There is something tricky about that. Yes.
Yeah, I mean, what's tricky is the transparent truth predicate wasn't brought in to do any work specific to sort of further our reach of arithmetical consequences. That's not why you have it. It's a completely see-through device, right?
I would disagree with that.
Oh, okay, that's right. We have, okay, sorry, fair enough. And I, from talking with you elsewhere, that's an interesting disagreement, but okay, maybe that's the important disagreement. So Lavinia, I learned from discussion, I take it some of you were in on her papers also. She actually thinks that the transparent truth predicate is brought in to serve the role of giving you higher order quantification in a first order language. I don't think that. But that's probably where we're just coming at this from very different things. So my point was, from my perspective, transparent truth predicate is just brought in to allow standard generalizations the way we normally have it, it's certainly not brought in to help us get more arithmetical consequences. Or any consequences of any particular theory. That is a job for stronger truth predicates. And that's why I just find that the sort of, I'm trying to get my head around the philosophical point of even Volcker's, some of Volcker's work. So this is me still trying to get my head around kind of the philosophical punch of some of this.
I think what you're pointing at is a debate on conservativity. Truth predicates should be conservative. You're saying something like that. I strongly disagree. First of all, because
Are you saying that?
I'm not saying that.
well, you
I
just
know
said
that that's a debate that
Well, yeah, I'm just trying to track this.
you just said it
Absolutely
shouldn't be
not.
brought up to prove more stuff for any theory.
Right, but
Any theory.
that's about its telos, not about whether it in fact does.
I know, but
Yeah.
if the thing is, okay, so what you're saying is, okay, so what? I mean, if one of them proves more than the other, so what? But this is not about, so there are two things here. First of all, it's not that one of them proves more than the other, therefore the first one is, the former is better than the last. That's not the argument. The argument is, in one of them, I can reason classically from induction, and in the other one, I can't. But induction is an arithmetical principle. And the whole thing started by saying that we can we can abandon classical logic, but that's going to affect only the semantic reasoning. Everything that is arithmetical, every arithmetical principle, will behave classically. So, and I think that is not being respected here, right? So we have an arithmetical principle, which is induction, and from that we can reason classically. Of course, it doesn't really matter how much induction truth theory proves. I won't evaluate the theory of truth in terms of how much induction they prove, but here, given the comparison, we can see that in one case, we can reason classically from induction, in the other one we can't. Because if we could reason classically from induction in this case, given the last comparison I made between the restricted things, we would have the same consequences.
I'm sorry, we need to move.
Yes, thank you.
Oh,
Thank you. Macaulay, Ferguson, please.
Oh, so when you announced in your slides that you were doing LP Circ, I immediately started looking at each of your steps as you're going through it with the question of how dependent your results were on the choice of the logic there. Because as far as the LFI community is concerned, I think LP Circ is sort of not really used very much. But I could never see any step that really sort of wouldn't have applied to any of the other LFIs, like the C systems or anything. So I guess I was curious if you thought while you're doing this about the generality, because an LFI person could, I think, easily just say, well, I mean, without going through the results, say, well, nobody cares about LP Circ anyway. Like we talked about that in a database context, but that's not the LFI bread and butter. So did you think at all about the generalization? Do you have any intuitions about how far this goes?
yeah, I mean, the other generalizations, I think, don't add anything that matters. I wanted to keep it simple. So if you add a new conditional, I mean, you can already define a very strong conditional using the consistency operator, right? You can also define a strong negation, and you can have whatever you want with the new thing in terms of connectives, right? Of course, you can have different consistency operators, you can add new conditionals in terms of other things, but I don't think that's going to change the theory, mainly because what we're trying to do here is axiomatize the fixed point models of LP, then those are formulated for LT, and LT already contains its own connectives, so we're going to have to use the same connective for that, and then we just want to say that the other side, I don't see the use of the other things that the other LFIs add in this case.
As I said, I didn't see any step that didn't immediately sort of carry over, but I didn't know if you had any thoughts on that.
So I read the whole thing and I thought, well, I mean, this one, I thought I didn't need it and I won't do any work, so why adding it? My LFI is a strong LFI in the sense of the authors, of creators of the LFI, so I thought, wow, this should be enough. But maybe it's not, but I don't see how that change things.
Thank you.
Thanks.
Patrick?
Let me return to the day point. Induction is not a classically valid principle. It's a principle about numbers.
Yeah.
So why we have to apply induction here to the truth predicate in the language? Maybe in your reply to JC, the argument is because we want a non-conservative theory of truth or something like that.
No.
So why we have to apply? Because the cocktail is really dangerous. You are using a consistent operator, what mean classical negation, transparent truth, plus PA.
The thing
We
is
know
consistent.
that altogether,
It's all consistent.
Because she loses
what?
transparency.
I
Yeah,
don't have transparency for the circle.
the cocktail, the philosophical initial cocktail is really dangerous. Yeah, because you have classical negation, what mean revenge,
Yes.
truth, maybe transparent truth, we have to discuss that, maybe not, and full induction.
But which paradox do you know that bears on induction? Like the diagonal lemma is provable without induction. So induction is not,
But
it's never given us any
the discussion
paradox.
here is if we want to apply full induction for the transparent truth or not.
Why
For me,
not?
it's not obvious.
But it won't give you a paradox. I mean, we could discuss why extend induction with near instances or not,
Yeah,
but that is not dangerous. I mean, the reason why there's there's no reason not to do that comes from the paradoxes.
well, you
Now you-
have a conditional that detach in the language.
But that has nothing to do. It doesn't give you, induction doesn't give you the I mean, the paradoxes are not dependent on induction at all. There are no paradoxes of induction so far. I tried to write a paper about it.
No, but the paradox, the Tarski's theorem say that you cannot apply in PA transparent truth in order to consider the truth predicate is part of the PA.
Yeah, but that holds also for Robinson arithmetic. Induction is doing nothing there. Robinson arithmetic proof, the diagonal lemma does not depend on induction at all. The proof goes through like with a couple of functions involved. I mean, there's nothing to do. You can actually have the diagonal lemma in primitive recursive arithmetic. So nothing here depends on induction. Now, we can still discuss why or not extend induction. Some people think of induction as a list, and some people think of induction as an open principle. I think of induction as an open principle. I think that if we're talking about numbers, then induction holds of every predicate you can think of, because I think that's part of concept of natural number. But if you don't, then you would just stay with the harpoon theorems, and it's fine. But I think, yeah, probably if you don't, this result doesn't affect you. But if you think that induction is a number theoretic principle, then you do have a problem. I don't see why you would reject an instance of induction, even if it contains the truth predicate. Even if you think the truth predicate is, even an LP. Like, why
Well,
would you?
In LP, you don't have strong negation.
So what? Induction holds anyways. Even if it's a predicate that always gets value 1/2, induction will hold.
Yeah, but you have to want all together. Classical negation.
Induction doesn't add any danger to anything here. Nothing bears on induction. No contradiction bears on induction. I swear to God. it doesn't work like that. It's not a cocktail.
Okay, unless anybody else has a further question. Okay, good.
Very quickly, Eduardo is going to talk later about this very fine distinction between theory and application. And sometimes the result of an application of theory is theory. Do you agree with that?
Can you give me an example?
Yes, sometimes I apply modus ponens as part of logic, and when I get is another principle of logic.
Yes.
So it goes back to the theory. Now, sometimes I apply a theoretical principle, and the results of the application take me outside of the realm of the theory. Like, for instance, applied math that will give me some truths about
Oh, I see.
economy
Yeah.
or about archery or something else. Doesn't have to be the result part of the theory from where the application came. And
Yes.
my question is simply, I suppose you don't contend that every application of a mathematical principle results in a mathematical member of the theory, of the mathematical theory. Now, in what sense, what we're missing here in the application of induction is really a loss of mathematical theory, even arithmetic, and not just the loss of an application that goes beyond the theory.
What do you think about this principle?
I would say that I don't know if that's mathematical or not,
Why not?
because depends on what those x's are.
I agree with you, I'm sorry.
What do you agree with?
With Picollo.
Why did you call it mathematical? That's like the
Until-
property of zero is omniscient or something. I mean, it depends on what you can substitute in for
Let's
the.
say it's a property that applies to natural numbers. Right?
Omniscient.
Like truth
No.
applies to natural numbers by default.
Being loved. Some people love natural numbers.
Well, if you love zero and if you love a number, then you love the following, you'll love all numbers. Right? If it's a property of natural, if that applies reasonably to natural numbers, then it should come through. I don't see. So, for instance, when you teach logic 1, you do an induction on the complexity of a formula. You apply induction.
No, but sorry, narrow couples of numbers are number theory.
Yeah, but
I think that the principle is giving you, I'm not saying that the property is number theory, and the principle tells you that whatever x is, if it can reasonably be applied to zero, you can show it's zero has it. It doesn't matter, it's not that the property is therefore part of arithmetic, it's the principle that is arithmetical, the whole principle, not
Yes,
the,
yes, just like modus ponens is logical, that doesn't mean that all the results of the
Exactly.
application are going to be logical.
I agree, but every instance of modus ponens is a logical, is a logical truth.
Yeah.
Well,
if
let's go for this. Every instance of this principle is a logical truth, right? Let's run with this. I like this one. All right. Every instance is a logical truth, which is not to say that, I don't know, Mexico is a country, therefore Mexico is a country. I mean, this is a logical truth, but it doesn't mean that Mexico is a logical object or that being a country is a logical predicate, but it's still a logical truth, right? Yes? Did I convince you?
Sorry.
this may help, but there's actually a similar discussion in the discussion on grounding and the discussion on truth making, things like that. And can I?
Yeah, sure.
So there's people asking like, what makes something of the form A or A or B
Yeah.
true? And they say, well, it has to be if one of these is true. And then so this, what does that mean for something like that? And there are some people who have actually argued that there are two camps, right? Some people who say like, oh yeah, what grounds this truth has to do with disjunction and negation. And others that I go, no, it's gonna be grounded by the fact that one of these is true, and whatever grounds those is gonna ground the whole thing. And it's the same thing here, right? I think, and that's why, since I love this explanation better than this explanation, okay, I'm sorry, Gil.
I just want to say, I think I'm sorry, I no longer agree with you. I want to say, I get that you want to call it an arithmetical truth, fine, no problem. But the debate really comes down to whether from that arithmetical truth, we ought to be able to detach no matter what goes into the x's. And that doesn't follow from the truth of it being an arithmetical
But
truth.
it follows from the motivation.
No.
Okay. It follows, yes, I totally agree, but it follows from the motivation that I gave at the beginning and said, well, if it's arithmetical, I reason classically with it. If you grant me that this is arithmetical, then you should be able to reason classically with it. Of course, reason just here, as you said before, just means that I can apply the classical rules. That is the point. But of course, one can, there were different ways of contending this, as we can see.
Okay, if nobody old has questions, I have a question. So I'm going to put myself on the list. Sorry if you still have time. Which is just, I mean, I can see the proof, and I think I agree with you. But again, coming from the philosophical, no, actually, it's a more logical point of view. Do you have an idea of what went wrong? Like what restriction didn't do its work and overreached?
Yes.
Yes.
So that's why I wanted to write it down a little bit. Where's the?
This or what? Or this?
I'm sorry. So basically you added axioms that said, or sequence that said that if phi is arithmetical, then phi is consistent.
Okay.
Right?
Mm-hmm.
But they didn't say that. It is a meta-linguistic
Yeah.
thing. But that was what. And then now you have instances of induction such as the following. Right?
Mm-hmm.
And this one is not arithmetical.
Yes.
So you don't have the consistency of this.
Okay.
And moreover, this thing has has a free variable there, right?
Mm-hmm.
And here you have a universal quantifier. So this condition will be true if all instances are true, right?
Mm-hmm.
It will be 1 if all instances are 1.
Okay.
But some instances won't be 1. Some instances, well, in this particular case, maybe it doesn't work. But let's assume the property holds, right?
Okay.
Some instances will be 1/2, right?
Mm-hmm.
And once an instance is 1/2, if all instances are either 1 or 1/2, and some are 1/2, then this thing is 1/2.
Okay.
And therefore, this conjunction, if this is true, so if these two things are true, but this one is 1/2, then the whole conjunction is 1/2. And then you cannot detach anymore, right?
Yes.
So that's what's going on. That's why Halbach and Nicolai say what you're ruining is schematic reasoning.
Yes.
So once you have schemata, then and according to my, as JC knows, my view on what truth does, this is no surprise, right? The truth predicate should allow you to reason schematically.
Yes. No. Yeah, that makes sense.
To overcome this.
Okay. Well, we have run out of time. But thank you, everybody. Muchas gracias a todos por estar aquí. Recuerden que después, bueno, agradecer a